Thank you for the introduction. So,
and you want what's your name?
I'm Reza, actually the first one. Let me just start.
Reza.
Yeah. Okay. So we see here. This is actually about CO2, and after Paris conference, they decided to restrict the global warming by 2 degrees C. This is a challenge actually for the world. And we know that one of the main challenges that we have to face is how to transport the existence of CO2 emission in the world. So one of the ways to transport CO2 is using pipelines. But of course, we don't want to repeat the same thing happening here and having a disaster and failure and then releasing CO2 in another manner. So in CO2 Quest project, which is a European project, we try to understand how is it possible to deal with these kind of fracture problems and what are the possibilities to solve this problem, because CO2 is quite different from natural gas because we transport them in dense space and it's really critical. I will talk more about this problem that we have with CO2 transportation. So in this presentation, first I will introduce the problem, then about the experimental setup, we talk about the experimental setup that we have to test our material, and then the modeling approach that we use to predict its behavior. Of course, I will try to do it in 15 minutes, which is quite difficult. So first, about the problem. We know that transporting CO2 from the capture plant, which is a part of CCS, to the storage area, which is also part of CCS, needs a tool, which is a pipeline. It can be a pipeline. In most of the cases, it's a pipeline. And as I said, we are trying to investigate how to approach avoiding any failure in the pipeline. So we need to come up with the concrete solutions to have a pipeline which does not fail. So to this end, in the CO2 Quest, we try to have some objectives from material point of view. First, we selected the material, then we developed a brittle fracture model to deal with the brittle fracture, and also we try to couple the brittle fracture with fluid properties. It means that we have CFT plus structural model, and at the end we try to investigate the effect of different impurities. Here I will cover the brittle fracture and also the coupling model that we use. So to this end, first we have to see is there any risk of brittle fracture in CO2 pipelines. As I said, we are transporting CO2 in dense space. So imagine that we have a small puncture, or if we have a small fracture and the CO2 gets into the soil which is surrounding the pipe. It's a buried pipe actually. And if we do a small calculation, it's missing, I don't know why, but it's a heat transfer equation that I used. So then if we model the temperature around the pipe after escaping the CO2 into the soil, we see that the wall temperature can get down to minus 80 degrees C, which is critical for pipeline seals. So we know that there is a risk of brittle fracture in that case. So how to deal with that? First, we need to characterize our material. So we do 2 types of tests. It's a Charpy test and drop tear test to characterize the material behavior. So here is the Charpy test setup that we use to characterize our material. We compare different materials, but here I just talk about the material that at the end we selected for this project, which was X70 API pipeline steel. So you see, for brittle fracture, we have quite low energy to break the material. Basically, the Charpy test is really well known. It's old school test that they use in the labs to break the material. It's just transformation of the, let's say, potential energy to kinematic energy, and we observe how much energy can be observed by our material. So we also have some scatter at low temperatures, which varies between sometimes 5 to 15 joule. So another way to deal with this material selection is a more realistic test, which is a drop tear test. Because the dimensions of Charpy tests are limited, but for drop tear tests, we can increase the thickness of the pipe to the real pipe that we use in reality. As you can see here, it's again, there's a height, we drop a weight, it's again the same concept, just transferring potential energy to kinematic energy and just measuring how much energy can be absorbed by our material. But in that case, we can also look into our material fracture surface to just see any transition from brittle to ductile fracture, as you can see here. This is a typical ductile behavior, which you have a blunting of the crack, it's non-fracture, and at the end we will have a tensile fracture. But if we go to the brittle fracture mode, we see a pure brittle fracture at -80, which is a flat fracture. So we are dealing, in this presentation, we are dealing with this type of fractures. So for the modeling, again, we have two approaches. For the pipe, we have CFD modeling, which simulates the behavior of the flow, and we have also XFEM approach, which models the crack inside our pipe, which I will explain later. So I don't know why the equations are missing. It's something wrong with the presentation or with the projector. But here we have some equation of states for the CO2. When the CO2 is being released from the pipe, then we have a fracture. We assume that we have a one-dimensional model to transfer actually the CO2, to release CO2 from the pipe, and output of these equations, which is a partial differential equation, would be a pressure, internal pressure change in the pipe, which we apply to the model that we have. So for fracture, we use XFEM approach. Again, equations are missing. This one not. We have different approaches to capture singularity and also to model crack propagation through the pipe. We need to have let's say, cost-effective model, which does not take a lot of time, which does not take a lot of memories, because we're coupling with the CFD model, and the time is really important factor here. So we use XFEM approach, which we add two extra functions to finite element method, the heaviside functions and crack tip functions, to capture singularity and separate the crack. So more explanation is beyond the scope of this presentation. Again, we use the sine function to detect the crack, and then we use the coexistence approach to model the crack behavior. Let's say we have two variables, which is the coexistence parameters, which the separation occurs and the damage accumulation occurs by time. So we apply the same approach to the lab scale test that we did to the Charpy test. You see here the mesh that we use for the Charpy test, and here is the result. We have a nice result. This part is not, we are not really proud of that, because it's just a wave transformation and the crack starts from here. So this is just the elastic part, but here we have some good correlation, let's say, to crack propagation. And also we apply that to here. You can see some results of stress distribution, how the crack propagates. And then the last part, worth mentioning that the last part, we have a mixed mode crack, because here, because of the impact, we have huge compressive stress there. So when the crack hits, the compressive stress wants to find some way to propagate, which would be in mixed mode. We did it also for the drop tier test. As you can see here, in this test, it's much more difficult to simulate exactly the same wave transformation after impact. But we generally have good agreement if we just integral the area and we measure the amount of energy. You see that we can almost predict the same amount of energy that we have in the experiments. A little bit higher energy observed here, because we have also some dissipation of energy at our contact, which we do not take into account. So again, the formulas are missing. I think you have seen enough formulas in the presentations. So here we just calculated the crack propagation speed versus dynamic stress intensity factor. We use this to calibrate our model. So we use the drop tier test to just calibrate the dynamic stress intensity factor, which is let's say a kind of the correlation between crack speed and the dynamic stress intensity factor. Then we apply the whole concept to a pipe. You see an example of the pipe here, the wall thickness of 18 millimeters, and it was 10-meter long pipe. So we used the symmetric model condition, and this is the initial crack length, so that we calculate the stress intensity, which is not here, and then crack velocity, and then we communicate with CFD code to predict or to calculate the internal pressure, and then we try to continue with this loop. Of course, we apply the backfill pressure as well, because with the backfill pressure, it's more realistic and it should be taken into account when you have a parent pipe. So, and then we can see some stress intensity at crack tip and the hook stress, which is the opening which is the cause of opening of the crack. And we see some small scale yielding, which is really important for brittle fractures, because we don't want to induce a lot of plasticity, so we have to be careful about that. And here you see that when the crack is the crack is propagating, the stresses are going down, which means that the effect of backfill pressure is really important. So when the crack is propagating, the hook stress is not increasing, it's also decreasing, because we have also backfill pressure which closes the crack. And here are some, the same thing that I said, the opening of the pipe. So at the end of the simulation, we have around, let's say, 400 millimeters, 40 centimeters opening of the pipe, 10 meters pipe. We also investigated the mixed mode crack propagation, so just to see that is there any possibility that the crack goes around the pipe, because if we have a mixed mode crack propagation, it means that in some cases the crack would be arrested before any propagation. So we could see different behavior inside the pipe. This is inside and this is outside of the pipe, because outside of the pipe we apply the backfill pressure, so the stress distribution is different. So we monitor the variation of stress intensity inside and outside of the pipe. And as you can see here, the stress intensity is decreasing by time. And also here we have I don't remember what was that, but I think it's a ratio between K1 and K2, which gives us some idea about the mixed mode behavior. Again, this one is working. So we try to calculate the crack propagation angle, and we just plot it against the normalized K2 variable. And here is inside the pipe, and here is outside of the pipe. And we see that the maximum and minimum deflection actually or crack propagation angle is limited. So there is no risk of mixed mode crack propagation. But the crack will be twisted at some certain points, because we have positive and negative stresses at crack tip. So again, we compared our prediction to some analytical approaches or some sort of empirical approaches, and which you see here, HLP plus CFD, which is empirical equations that we use to compare, and also XFEM plus CFD. And you see here the XFEM plus CFD are in line with the prediction of the analytical approaches at low actually energies for brittle fractures. So at the this one works actually. If we have a pipeline and we are concerned about the fracture, brittle fracture, this is the first time that the live coyote actually captures the road runner, because if we plot them against each other, if we say this is the behavior of CO2 including some impurities, and this is some sort of behavior of crack propagation in combination with CFD model, we see that there is a drop, and then after a certain while, the speed of let's say the gas decompression and the CFD model predicts the same speed, and at that time the crack will be arrested. So there won't be any problem of crack propagation. So I think that's all that I wanted to say, and also I would like to thank the European Union for providing the financial support, and of course they are not responsible for these bad equations that I showed. Thank you.